So, if you're interested in quantum physics, you've probably seen this equation before. It's pretty famous. It was written on Evelyn Schrodinger's grave itself, and it's Schrodinger's equation. It's used in quantum physics. But before we get into quantum, like the quantum physics and the weirdness, the oddity of quantum physics, we need to get into quantum physics 101. So, classical physics is the way something moves. So if you have a tennis ball, the nature of this ball, the way it reacts to other forces around it, and the way it moves, and it is subject to Newton's laws and stuff. So if you put a force, it'll be in motion, blah, blah, blah. That's classical mechanics. It's how things that are all around you work, like bikes, wheels, tables, stuff like that. But if you zoom in on this baseball, then you're going to see its components of rubber and cowhide. And if you zoom in on the rubber, you're going to see like the components of rubber, like ozone and stuff. And then if you zoom in on the ozone, you're going to see an oxygen atom. So an oxygen atom is the first stage of quantum mechanics. And it's where something weird happens. It's where it's not subject to all of the laws of classical mechanics. So subatomic particles are even weirder than atoms. So this is what a hydrogen atom looks like. Proton, and this is electron. H. And so if you take the electron, for example, so you take the electron, this is what you picture an electron. It's just a dot. It's a very, very small dot. But someone came up with a interpretation of how we should actually look at this. Because no one's ever really saw an electron clearly. You just have electron microscopes, just little dots all around. So he came up with a quantum wave function. Quantum wave functions can look like waves, Like kind of like that maybe. Maybe it's 0 at this point. Go up again. It's usually how a quantum wave function looks for an average particle. And they're usually represented by either this symbol, which is actually for electroflux, or this symbol. The most commonly is the second symbol. This is psi, PSI. And that's capital psi, and this is lowercase psi. So psi is a Greek letter for, I forgot what psi is for, but in math and physics, it represents quantum wave function. And what do they do though? Well, quantum wave functions find the probability density of where an electron is going to be at a certain point. So for the chances of this electron subject to this corresponding psi or quantum wave function, if it's going to be right here, is the amplitude squared. So the amplitude squared, the A squared. So right now, let's say this was 3 right here, and this was 2 right here, and this was 1 right here. And then you would see that the amplitude here is 2. So that's just going to be 4. That should give you a sense of the probability density of the particle. So just taking psi squared, and you get the exact probability density of where it's going to be at any given point. So you get that, and she's like, how do we prove this? What are we gonna do to prove it? How will we make people believe this? Because it is pretty weird. And if someone in 1929 came out to me and said, hey, did you know that particles actually are waves? I would be like, you're crazy. But he did something called the double slit experiment. So he put a wall like this, kind of, and he put another wall like this. And over here was an electron shooter. It looks like that. So this thing shoots electrons, and the wall in front had two slits. So if particles, so this guy thought if particles were waves, they would go like the electrons would go like this, kind of like a longitudinal wave, and then over here it would result in wave interference. What? If we do this, there's wave interference right here. And if there was wave interference, then it would create multiple stripes over here, multiple patterns of electrons, which is one of the weird things about, because if we took a dog like Scooby over there, then Scooby have fleas? No, she doesn't. It wouldn't, Scooby over there wouldn't be defined as a quantum wave function. She wouldn't even be described as there's no such thing as a classical wave function. She's not a wave. So that explains why if you have a paintball gun and you do the same experiment except with a paintball gun, and you shot it like, I don't know, what color is this? Royal blue paint everywhere. Paintball gun. Then it would like go in random places, like maybe one over here, maybe one over here, maybe one over here, be over here, and a few over here, here. So it would just be just unpredictable, but not like the electrons over here. And so the most confusing thing when I saw this equation, when I first saw this equation, was a wave function. But the second most confusing thing was this thing. It's a triangle and it's squared. So you might recognize this triangle. It's the del operator in nabla. And if you saw my videos on electromagnetics and Maxwell's equations, before I did a video about Coulomb divergence, and they're over my delta times F and delta dot F, Coulomb divergence. And you might remember that the del operator is equal to the sum where I equals 1, infinity, or no, n, not infinity, we don't need infinity though. And there's v to the n, partial, what am I thinking? Equals the sum of ni equals 1, and of partial over partial v I, and that is nabla, where v is a variable. If variable 1 might be x, variable 2 might be y, variable 3 might be z, variable 4 might be w, and it stops at variable n. And that, I forgot. V hat. So that's a unit vector, by the way. So this would be equal to how, say, if the vector function was 3-dimensional, then you would have partial over partial x, partial over partial y, partial over partial z. And that's where the gradient of a vector field is just equal to just taking the partial derivatives of all the components and smacking them into a vector function. And so this is equals sometimes represented by this, and this is the divergence of the gradients. So today we're going to talk about a quick review on divergence, and we're going to talk about gradient too. So divergence first. So you have the vector field F. And let's say there's an electron here. Gauss's law, if you saw my last video on maximum equation, you would know Gauss's law that states that the electric charge of a particle is equal to the divergence of the electric flux density. Bing bong, bing bing bong. And that's an electron there. That's placed in an electric field. And the divergence of this, F, would be equal to partial Fx over partial x plus partial Fy over partial y. I did an example of this in the video before last. And, or partial Fz over partial z. Notice how we didn't put unit vectors at the end of this, so this would not be equal to this. It would not be a vector function. And so that's divergence, but gradient we have to talk about more since we didn't know what to do a video on this. So let's say we have a vector field. Let's do the physical interpretation of gradient. That's too, But yeah, let's do the physical interpretation. So let's say we have a vector field, or not a vector field, just something. Should we do a physical interpretation on that?
Whatever you want. You're at 13 minutes.
Let's not. And, well, so gradient of F, you might already know what this is, even if you don't know what the heck gradient is, you know what nabla is, so multiplying a vector function times a scalar would just give you the x component of the vector function times that scalar, y component of the vector function times that scalar, z component, if there is one, of a vector component times that scalar. Or if there is one, t component of a vector function times that scalar. And this is equal to partial fx over partial x hat plus partial fy over partial y hat plus partial fz over partial z hat. So the divergence equations and the gradient equations are very similar. The only difference are the x hat, y hat, and z hat, and they're unit vectors. So right here, this is not equal to a vector function, but right here it is equal to. It's equal to partial fx over partial x, partial fy over partial y. If there is one, a z component, partial of z over partial z. And that is gradient. But the Laplacian operator is something different. The divergence of the gradient. So let's do an example. Let's do the Laplacian of f. F is equal to. Do you want it to be 2-dimensional or 3-dimensional?
It's up to you. You're at 15 minutes.
two-dimensional. So 2x plus 3 and 3y plus 2. 2x. Let's put some x in where I can put it. And so this would be the divergence of the gradient. So order of operations, basic guys, we have to do the gradient first. So finding the gradient, the formula for gradient is this. X hat plus partial fy of partial y hat. So right now we have 2 dimensions, so it's only x hat and y hat. So this would be partial f equals partial over partial x of 2x plus 3 x hat. Plus, and since this the first term isn't multivariable, we can just change it to d over dx, 2x plus 3, x hat, plus partial over partial y of 3y plus 2x. Now, I can't say the same for the first term as we can for the second term, because this is multivariable, and this one is not. And so taking the derivative and partial derivative of these terms gives us 3 goes to 0 since it's a constant, 2x goes to 1 since it's a constant, so that's left us with 2. 2 plus and partial over partial y. This is treated like a constant, and 2 times any constant is a constant, so this goes to 0. Y goes to 1, so that's 3, so it's 6. 2 plus 3 is 6. That was a joke. Okay. 2 plus 3 is 5. And, so it's 5. The Laplacian of f is 5. Let's do another one this time with that's gonna actually give us a that has a Laplacian of Laplacian of a function has variables in it, because it's not always gonna be a scalar. There's gonna have some variables in it. So let's do f equals trigonometric functions that will fail me. Sine of x squared x y and cosine of y 2 cosine of y, and that's a trigonometric function with that's a vector function with trigonometric functions. They're my favorite ones, and so they go down to partial f x over partial x hat, not x hat, I'm sorry, plus partial f y over partial y plus partial f z over partial z. And they're all squared, by the way. Squared, 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 squared. And, so this is going to be equal to, sine, so many exponents today. Cosine squared of y, and this is going to be equal to sine squared of xy is going to go down to 2 times negative 2 cosine of xy plus sine of cosine squared is going to be not negative, I'm sorry, plus minus plus negative sine of negative, oh my god, I'm doing the negative 2 sine of y, and this is going to go down to 2 cosine of xy minus 2 sine, 4 sine of y, 4 sine of y, because 2 is 4, and that's a Laplacian right there. So you can find it at any point. And another one. V, by the way, is potential energy. You know that V equals mgh. Equals mgh, and psi, just explain to you the imaginary number you probably already know. Planck's, what is Planck's constant? Which is h over 2 pi. Well, h is the Planck's constant, and so that was pretty quick. Partial and partial over partial t is the time derivative, partial time derivative of psi. So this thing on boards is negative the reduced Planck's constant squared over 2 times the mass of the particle times the Laplacian of psi of the wave function, of the quantum wave function, plus the potential energy times the quantum wave function, plus the imaginary unit times the reduced Planck's constant times the time derivative of the quantum wave function. That was Schrödinger equation right there. And there's the double slit experiment too. With that. And now I have 2 things to ask you. One or two.
Louie, you're over 23 minutes.
I'm over 23 minutes. Oh shit. Okay, one then. So there was a equation I derived last night, and if you guys see any flaws, then report them to me, and I'll consider it and change my equation. So it has to be rectangular. This thing only works for rectangular prisms, guys, by the way. And so Gauss's law, as we know, states that Gauss's law, the other Gauss's law, not the Gauss's law of electrostatics. The electric flux is equal to Q over epsilon naught. Now, I derived this equation last night, so it might not be correct. So if you guys see any flaws, just report them to me. So we're taking why did I do that? Of E dot dA is equal to the electric flux density, the electric charge density times the volume, because since, let's say we have an electric flux charge density D, and it's equal to charge per unit volume, that means dV is equal to Q over epsilon naught. That means that, well, S is the volume. S is the surface of the rectangular prism, by the way. Is equal to D times LWH which is the volume, L length times the width times height, over epsilon naught, the permittivity of free space. And if E is parallel to dA, then it's going to be equal to EDA equals dLWH over epsilon naught. And we have E times the surface integral of dA equals dLWH over epsilon naught. And we have this is going to equal to the surface area. Going to have 2ELW plus 2ELH plus 2EWH is equal to dLWH over epsilon naught. And then we have these cross out for the L over here. These cancel out for the W over here. And these cancel out for the H's over here. So we're left with 6E is equal to D over epsilon naught. So 6E is equal to 1 over epsilon naught times D. And like we said before, D equals Q over V, dV equals Q. So that means, if we multiply V to D, we're going to get Q enclosed. So, Q. That means E divided by 6 on both sides, and you multiply by V on both sides. EV is equal to 1 over 6 epsilon naught times Q. Q enclosed. And multiplying E times V gets us to this. Of course, basic physics, guys. Triple integral integrated over a volume V. The volume V is inside of S, bounded by S, of E dot du, where du is an infinitesimally small cube, like 0.0001 nanometers, and that's equal to 1 over 6 epsilon naught times Q enclosed. And we know that yeah. So that's it. That's my derivation of Gauss's law not Gauss's law last time, but Gauss's law. And if you see any flaws, please put it down in the comments or something. I don't know. So, yeah. I'm done.